This is about using large language models to analyze wireless protocol data, specifically Bluetooth and Wi-Fi. So interested in the bits, not so much the RF signal. And this is going to focus on a specific implementation, which is this script in the wireless examples repository. So first, there's the fundamental question of, can large language models resolve wireless communication issues, and what exactly are we looking at for questions? Often with wireless communication, the questions aren't so much about the communication itself or the wireless itself, but it's about the devices using the wireless. So, for example, if you have, let's say, Bluetooth being used for headsets or smart devices, sensors like watches, the question may be, why is it not visible when trying to pair with my phone? Or it might be visibility with Wi-Fi devices. So why can't I see my device on my home Wi-Fi network? Other questions could be, oh, what about devices sending unnecessary packets? Or what about devices interfering with each other? Or could be more focused questions on privacy, like how private are these device transmissions, or how easy is it to fingerprint devices? So, a lot of these questions involve the device itself, but rely to get an answer on understanding the wireless communications going on between them. And large language models have the potential to be able to break down these questions about devices into questions, specific questions of wireless communication and what's happening there. So a little more detail on this. If we're looking at how to analyze some of those questions, two broad categories. One is, try to use a large language model to answer the questions, or a custom rule-based system that has hard-coded rules on trying to do specific types of analysis. And wireless communications is particularly difficult for analysis because the packets aren't homogeneous. So ideally, when doing statistical or other types of analysis, it's nice to be able to have your data elements as kind of like rows in a spreadsheet, where each row has the same columns of data, of elements of data in it as other rows. With wireless communications, that isn't the case because packets the information they have really can differ between technologies. So the data that's in a Wi-Fi packet can be much different than the data in a Bluetooth packet. And even within that technology, within the Wi-Fi or Bluetooth, packets can really differ in the types of data that they have. So a advertising packet in Bluetooth will have different data than a audio packet with streaming data in Bluetooth. Also, if you look at one particular packet, its data tends to be hierarchical. So packets, their data is organized into multiple layers nested within each other to be able to make processing orthogonal at the different layers. So being able to have independent code processing each of those layers, which allows for more plug and play. But it can make analysis difficult because all of those different layers are within that one packet. Also, the components aren't always labeled consistently. So, what one technology may call the received signal strength of that packet, so how much RF energy it had, RSSI, another may call it antenna signal strength. So, there's that. If you're going to compare data from Wi-Fi and Bluetooth, there's could be difficulties in not having consistent labels between those two standards. And that's really, while that makes a custom rule-based system difficult, that's really where large language models shine, because one is they've been trained on large amounts of relevant data, such as the wireless protocol standards, communication, about where people have talked about how to troubleshoot wireless systems, and then also just wireless protocol theory. So all of these, it at least makes it reasonable to assume or to test how good large language models are at being able to analyze wireless systems. Now, if we look at some of these packets to better understand what the data looks like, we can see some of the previous slides examples illustrated. One is so we have here on the left a Bluetooth packet and on the right a Wi-Fi packet. And these packets were captured from over-the-air software using a Teledyne LaCroix wireless protocol suite software. If we look at these to compare them, we can see the different layers. So these are the signal layers, and then we have the multiple layers here of sort of the outer layer in the Bluetooth packet that has its address and what its connection information is and error checking, and then a more internal layer, and this is a type of advertising packet and it has information about that. Well, the Wi-Fi packet looks really different as far as not only from its internal layers, the wrapper layers, but also the internal data layers too. So a lot of different fields. And the other thing is the fields that are common. So for example, the signal strength we have on the Bluetooth packet, it's called RSSI. And here for the Wi-Fi, it's called antenna signal strength. And then also information about the channels is different too for the naming convention. So you have these very different packets, and then also the devices may be sending out thousands of these packets. So while a large language model would be great for being able to analyze these, you can't just stuff all of the data into the packet data into the prompt, because you're talking hundreds of thousands to millions of packets, which would exceed the size of even the very large prompts. So what's another way to deal with this? And this is what the script, the LLM guided stat analysis demo script, is an example of. So of how to get around this issue of being able to have to analyze large amounts of packets. So the basic flow is that the user asks a question, and for this example, are going to ask a specific question of comparing the number of Bluetooth advertising packets to a number of 802.11 Wi-Fi packets. So which were the most common and what are some of the interesting features about them? So this is the user question. And what we have here is the captured data. So the Bluetooth and Wi-Fi data was pre-captured and it's sitting on a laptop as stored data. And the script is going to take that user question and a catalog of tools, so a text description of what tools the LLM can use to analyze it, and it's going to take a summary of those tables, because this data is millions of packets. They're not going to be able to send all of this to the large language model. But we will send the question, the description of the tools the large language model can use, and a summary of the data tables. And it's going to create an analysis plan. And that data analysis plan will then be executed on the laptop where all the data is, all those packets. And those results are then going to be summarized and so they'll be sent back to the LLM, summarized, and then by the LLM to create a final answer, which is then given to the user. And that's what this script does. And the rest of the steps of this presentation will be going through these steps. So the first step was that capture and summarize the data. So, for example, could have a let's say people using Bluetooth, and there could be a Wi-Fi connectivity with the car, with the phone, and so if having a so have an analyzer. In this case, it's a Teledyne LaCroix X500E analyzer that's used to capture the over-the-air data as these communications are taking place, and that's captured with this protocol software. Now, this protocol software has a specific format of its data files, and so we use a script to convert those to a more common PCAP-NG file or file format that Python tools such as Scapy can then use. And so Scapy will look at the data of the Wi-Fi and Bluetooth data, and with the script, convert it to data tables that can be then used for the processing in Parquet, and then also create a table summary of what this data is, which is what is sent up to the large language model. Now, looking at what this summary is, so it's in JSON format, and it's basically a summary of the columns of those data tables that is something that the large language model can then use. So it has a description. This is an example of it, of two of the columns of the data table. So for numeric columns, such as the received signal strength, it has things like the name, information about the table, about how many counts of data there are, what the sort of range of values are, and statistical information about it. And then also some of the columns that are objects or strings of information. And in this case, it's summary data. So these are how the layers are stacked up. This column has that. So for example, this is a Bluetooth um, stacking of layers. So we have the Bluetooth RF layer and then the Bluetooth LE layer, which is on top of that, and this advertising layer, and then a specific type of advertising packet, which is a non-connection packet. And so this summarizes some of those and then other values that are in there to give, so it gives examples of other values in that table. And this would be a Wi-Fi packet that's similarly showing what the layers look like. So all of this is then given to the large language model to help it form a data analysis plan. So that table summary that we saw is sent to the create that analysis plan, along with the user question it had talked about, and then a tool catalog, which is describing what the tools that the LLM can tell the laptop to do for the analysis. And all of that is the LLM creates a plan in the JSON format for the laptop, that script to then use to do the analysis. There's also something called role information, and that sort of helps package everything together, and it sets the LLM's direction for the creating the plan. So in this case, that role information includes developer prompt information saying to the LLM that it's a wireless packet analytics planner, and then it includes that user, the prompt, which has information about the tools that it can, about what it should do and how it should create the plan. So this has information with what its tooling capability is, and then also the data sets that are available to it. So that will be the summary of the columns, and then also that user question. So if we look a little more, there's also included in that is the tool catalog section with further details about it, the tooling. And so it says that it has the ability to look at the counts, some statistical tooling, and then also some of the others for being what the columns that it will need to be able to process, and then some of the formats. So outputted, taking all of that in. The LLM outputs in JSON an analysis plan that the script is going to use to do the analysis. And so this analysis plan is telling the script, oh, this is the data set to use, and then also what it wants it to do for grouping by, and then what metrics to find. And all of this will be run and then returned back to the LLM for the final report. So that gets to the next part of the script of executing the analysis plan. And in this case, we have those data tables, so that and the which are available on the laptop, and then the table summary and that analysis plan. And so the script runs through all of that, creating the table summary and then the tool execution results. So the table summary is a unstructured text, and then the tool execution results are in JSON. And both of those are then sent back to the LLM, and this is what they look like. So the execution plan analysis, you have the table, what the layers of the table are, and some of the statistics that were calculated based on what tooling was available. And then also with the tool execution results, some of the specifics about that. So all of this is sent by the script back to the large language model. And that large language model takes those two items along with the roles for doing the summarization and final answer, and saying to write a concise report with these sections. And then it also has the user role, which has this information in it, and out will come a report. And to look at that, the report with the so with this model, this was using the GPT-5o Nano, which is a very in minimal mode. And it's interesting to compare this against a larger model, but we can first see here's the summary, key findings, anomaly assessment, and suggested next steps. I highlighted what I thought was interesting with the anomaly assessment, that it was suggested that the Bluetooth advertising prevalence, which it was, and it's very summarizing as far as very focused on what's happening and not very abstract. It does give suggested next steps with some kind of which I think is useful, about creating some graphical displays and then the reports. What's interesting is comparing this with the GPT-5.4 in medium mode. And you see again summary, key findings, and then interesting features and anomaly assessment. It's interesting that there were no next steps like in the minimal model. The 5.4 is a little more abstract with its summaries, as far as and I think a little able to better summarize, let's say with key findings, saying that the advertisements, it points out that they were generally weak, talking about the received signal strength with variations. Here, this we don't really see a lot of talk in the previous model, in the smaller model, about that. More of just a very specific summary of the data. I mean, we see that the RSSI is mentioned here, and also this talks about some of the filtering, about some of the issues that with doing the filtering, and we don't see a lot of that in the smaller model. So it's interesting. I think both of them are pretty helpful for answering the question about the most common, that they identify that it's the Bluetooth advertising packets, and talking about what they saw for the details and things like signal strength, where I think the 5.4 model did a better job of saying some interesting features that were available or were found with the data analysis the 5.0 lacks. So, kind of summarizing the script, I think the script shows with the models, this example, that there is potential for analyzing the direct analysis of multi-protocol wireless captures and being able to summarize it. There's some interesting directions for taking this type of analysis in the script as far as expanding the statistical capabilities. Right now, the statistical capabilities are very limited. Also, what's the best way to summarize the table information of all that packet data to send up to the large language model? So that's another interesting question. The ability for multi-step analysis, maybe doing multiple runs through where the LLM can then look at the analysis results and then ask for more analysis to be done by the laptop. So multiple steps might really improve things, especially for breaking down those higher level questions about why is a device not able to see another device. And also looking at some very answers to specific questions and then the cost to analyze to answer those. So, for example, the two reports that showed there, you can see that the comparison of the tokens and the pricing, that there's a pretty large price difference. So this is for that and the analysis step of when the LLM is creating the plan versus the summarization step when the LLM is then summarizing the results. And while the costs themselves are low for the one run, you can see that there's kind of orders of magnitude difference in pricing between the 5.0 and 5.4. So one of the questions is that 5.4's what I considered better answers orders of magnitude better, or could you do better by having a few more queries and analysis, multi-step approach with the cheaper model? So there's kind of some very interesting engineering questions there. So we'll look at the script code, and that can be found in the WPS examples repository. And then if you go down to the use case and LLM RAG, the script is right here. Now, this assumes that a Python environment's been set up. So, for example, using UV and then pip installing this requirements file. So once that's done, go back to the script, can run the script. We'll go through the document on it. So there's a README docs that we have actually right here that goes through the setup of what is talked about in the presentation. So this README has the information on the setup, and then also for using an open AI API key for setting that up. And then with the JSON config file, how to run with that, and I'll show an example again at the end, but that's what I had used. So for the configuration, this gives for that JSON config file, you can either put the config information at the command line with dashes or in the config file, and then this goes and shows just information about setting that up on the Open API. I like to use for the Open API key not to put it in the config file, but instead to make it an environment variable. Skip over the mocking. So the setup of creating the data files that was shown in the presentation, that's these steps of preparing the capture, running the code there for PCAPMG, creating that, creating the summary information for those table summaries. And then this gives some examples. So it can either just run a question, assuming you have the config files set up. And then this is an example with OpenAPI or OpenAI. So making sure that the key value's been exported before running it. And then this is the use case that I had used. And in here, so I created, this is all relative to the WPS examples directory, and then had the config file. So created a temp directory in here, which is ignored on Git. And then this information pointed to the config directory, which is right here. And this JSON file is right here. So basically set up, this was the question in the comparing advertising packets to Bluetooth to 802.11 Wi-Fi beacon packets. And then this just provides information of the data directory, the planner, so using LLM, using OpenAI. This sets the model here, and then the reasoning effort and the output directory. The logging information is pretty important for debugging. So log level of debug for the most information, info for just regular information so your logs aren't too large, and then just where to log the information. And then this was if you're doing mocking, which I didn't go over. But this is a good way to do testing. And then if we go back to the README, when we go to run the README, so pointing to that, and then run the script, and the script will run, it's running over the data that was put in the config files, which is all right here. It's going to then write out for the information. It will then write out the values and then place those in the artifacts directory. Then the log files generated, and just to show what the log file looks like. So when you go to run to start, so this was after it had ended, this was another run that if you're having to debug, can be able to just look through the log file and then just run the see what the config was used. It's always good to make sure that your OpenAI API key, try to make sure it's always redacted, but to look over any log file they're going to send to somebody just to verify that. And then this just has all the information. You can see what it was doing as far as the setting up the question with the analysis, and then sending this to the to OpenAI. So this is sent, and you can see the long responses. So the request, so sending the post information to OpenAI. This is good to debug in case something didn't work right. A lot of times OpenAI's messages are very detailed, and they'll just reply back what it was. But here we can see that it received the OK, and then this is the information that it sent back. And also you can get information as far as the prompt tokens. And then so this was saying that there were errors in it. So, and then it was sent back the information. We can then see when it does get returned. So in this case, that it was completed, the parsing was completed successfully, and then and that in this case we can see that when it was run, and you can see the values that were then sent, and basically then going back to, you can then see also the raw responses from OpenAI here. So this is just another way to debug what the output is, besides looking at the files that show up in the artifacts directory for doing debugging.